So you can see that 1 electron volt of energy, while it can get an electron moving pretty fast, it wouldn't be very good at pitching a baseball. Now, let's work on the wavelength. We're going to find the wavelength using our equation of lambda equals h over mv. So, lambda equals h over mv. For our electron, I should say, since we found our velocity in meters per second, we're going to be using the joule version for h. Velocity can also be represented in like parts of c, like a percentage of the speed of light. That's what you use when you're dealing with electron volts. But for now, we're just sticking with our traditional joules and seconds. For the electron, we get the wavelength of our electron is equal to 6.63 times 10 to the minus 34 joule seconds, divided by 9.11, 10 to the minus 31 kilograms, times 5.9, 10 to the 5 meters per second. We get a wavelength for our electron of 1.2 times 10 to the minus 9 meters. Try the rest, try to find the other two on your own. Now, electrons actually produced an observable diffraction pattern that was very similar to what was seen by X-rays, like a wave, when they were shot through what I think is nitrogen oxide. Then you can think of them as a superposition of multiple fundamental waves. An X-ray diffraction pattern would look like. The X-ray diffraction, essentially a bunch of waves acting in the same way to give a bigger, more complicated wave. They're very similar. If you only have one wavelength, idea that electrons then you're able to exactly determine the momentum. Therefore, massive particles can have a wave nature. Neutrons actually give something very similar as well, showing that it's not only the electron. P is equal to h over lambda. However, this provides no information about position. Now let's go back to that slit experiment that we were doing before. We have electrons traveling through a single slit. We want information about the electron's position and velocity. The electron is most likely to hit somewhere in the central maximum. So here, the big bright spot. Ideally, there would be a small slit opening and a small central maximum. This way we would know that the electron could only be going straight and it would hit a specific position. That would let us know its exact position, and we would also know the distance traveled so we could find the velocity. If the slit is larger, then the electron can hit the central maximum from multiple paths. So if the slit is really large, then the electron could take this straight path, or it could go something like that, or that. In that case, we don't know the exact length that it is traveling. it's got an x and a y velocity component, of which we can't really find. This leads to an uncertainty in the velocity. So we want this to be really small because then the electron can only go straight, and we know the exact length that it traveled. However, if you go back to chapter 17, you may or may not remember that the smaller the slit is, the larger the central maximum. So as the slit gets smaller, the central maximum gets bigger. What this means is that we can either know the velocity of the electron, or we can know its final position. But we cannot know both. This idea is characterized by the uncertainty principle. That's written out as delta x times delta p in the x is greater than or equal to h over 4 pi. So the uncertainty in the x times the uncertainty in the momentum is greater than or equal to this constant. We can also relate this to energy. Another expression of writing that out is delta E times delta T is greater than or equal to h over 4 pi. The uncertainty principle is weird. So essentially, we can either know the velocity of a particle, and the velocity is directly correlated to its momentum. So we can either know a particle's momentum, or we can know its position, but we cannot know both. That is going to do it for chapter 28. I hope that this made sense.